The most important algorithm ever? This is it. This is the code. This is Google. 8 lines of code runs 90% of the internet. Guys, how you guys doing? I'm really excited about the stream today. I think there's a lot of cool tech that we all take for granted, that we all treat as like a black box. I kind of want to like open the box, I guess, for some of the stuff that I feel like I have a somewhat of an understanding on. One of the black boxes I really want to get into is that I really feel like we really take Google for granted. I know a lot of people say like, oh, Google's really shit now. Google is just a page to redirect you to Reddit and Quora, which I completely understand and completely agree with now. Like, I don't completely attribute that to Google. I think that's more about how the structure of the internet has really redirected us to 7 social media sites, but that's not nor here or there. I think one thing people really don't talk about enough is how revolutionary Google's PageRank search algorithm was in the means of like searching online. It's not an understatement to say that this algorithm, sole algorithm, is $1 trillion algorithm. Pretty much any search engine you have now, like probably is going to use a variation of this algorithm. So like one thing I really wanted to do today, I really wanted to go into kind of the history of how this algorithm kind of rose about, talk about like the math of why this works at all, and then after that do like a kind of a demo. I originally thought to do a PowerPoint for this, but I realized some people graciously made some beautiful videos. I'm actually gonna watch along and get my insight reaction of these videos. Here we go. All right, so we have a nice video styled how Google's PageRank algorithm works. These videos I remember watching a while ago. I don't remember a lot from them. I remember liking them a lot. So we're just going to rewatch them. I'm going to get my insights on them too as something pops up. And yeah, that's where we're going to go today.
How does Google determine what order to show you your results? One of
Valid question.
the most important algorithms Google uses to do this is called PageRank. And it's an algorithm that attempts to estimate the importance of a website. What does it mean for a website to be important?
Which is a very fair question to ask, right? How do you consider which site is more important than the other?
Well, the web consists of pages, and those pages can be connected to one another via links. And the PageRank algorithm generally assumes that if many other pages are linking to a particular page, then that page is probably important. So a web page that is linked to more would be considered more important than a web page that is linked to less.
My first assumption would be that you solely do this based off just how big the node is, like how many people just go to that specific node. But when you really think about it, I guess that's really not enough, right? You got the Google example. If like millions of people go to Google, but then from Google, people immediately, almost always go to this one Reddit page. And then like these 10 other places also go to Reddit. Would you really say that Google's more important than Reddit? If everywhere you just end up back at Reddit anyway from all these different web pages?
But there's a problem with that approach. The problem is that it's easy for someone to artificially inflate their own web page's importance.
That's true.
If I wanted to make my web page seem more important in the eyes of PageRank, for example, I could just create lots of other pages that all linked to my website. Using that strategy, I could make my website seem as important as I wanted it to be.
Well, yeah. So it's not about the number per se. It's about the, the strength of the connection.
To really define what it means for a page to be important, we need to nuance our definition a little bit more. A page is more important the more it is linked to by other important pages. But this definition seems a bit circular. How
Bit
do we
recursive.
calculate a page's importance if doing so requires knowing the importance of other pages? Well, one way to calculate this is using what's known as the random surfer model. The idea is this. Imagine someone browsing the web. They begin on some page, chosen at random, and then they randomly pick a link from that page to another page that they visit. The random surfer keeps repeating this process. Pick a link randomly, visit a new page, pick another link, visit another page. The idea now is that we will keep score. We'll maintain a count of how many times
visits.
the random surfer visits each page. Each time they land on a new page, we'll update that page's score. Pages that have more links to them are more likely to be visited, so they'll eventually have higher scores. And because those pages are more likely to be visited, the pages they link to are also more likely to be visited. So a link from a more important page will matter more than a link from a less important page. After we continue this process for a while, we can take a look at the resulting scores and calculate what percent of the total score
of the visits,
score is. This gives us some measure for the relative importance of these pages, represented as what percent of the time a random surfer on the internet can be expected to be on that page. There's still one problem with this approach, though, and it's the fact that pages on the internet might not all be connected to each other.
Oh, that's true. You might have a bunch of islands, but how many? I guess that's possible, like in the past, but is that really possible really now? Here's what I'm thinking, right? If a site doesn't link, because you have the big tree, and the big tree is going to have your Reddits, your YouTubes, your whatevers, right? And then, like, if you have a site that doesn't link to that big community, I'm probably going to assume it's a small site anyway. Like, can someone name me the bigger island on the internet that... No, wait, never mind. I just answered my own question. Yeah, of course, there's another community. Probably not for, normal consumption. I guess I can imagine like dark websites like have a huge community, that don't link to other, the main island hub of different pages, which I guess makes sense. It's like that by design. So no, it's fair. I talked myself out of it. Never mind. I'm stupid.
A network of pages like this, for example. If we randomly start on this page, and we keep following links, we'll only ever visit one set of pages on the web.
Well, you gotta do it multiple times and get a percentage chance at starting a specific page.
Completely ignoring the rest of the internet, since none of the other pages are reachable via any of the links from the pages we're currently visiting. So to solve this problem, we need to occasionally reset our random web surfing. We do this by introducing what's called a damping factor. If the damping factor is 0.85, for example, that means that 85% of the time, our random surfer will follow a link from the page they're currently on, as they were doing before. 15% of the time, though, our random surfer will instead switch to a page on the internet chosen completely at random. With enough time, this ensures that we'll eventually explore all parts of...
I guess that is like how normal people do. You'll be on YouTube, click a bunch of things, and you'll go on a random anime Reddit, right? I guess that makes sense, yeah. That is the random surfer model. Because my solution was just have a simulation where you just run it like a million iterations. But I guess that would take longer. Yeah, that'd take a lot longer because to get it any accurate at all, you had to run like a bunch of simulations. But this way you can just run one long sim. You just have an appropriate enough damping factor, because it's either one damping factor or you need to know the number of sims, the number of iterations, and the initial probabilities of being at each page, which is 3 whole factors instead of just one damping factor. So I guess it makes sense. Yeah, that's smart.
Work of web pages and not get stuck at one.
Again, this only works if you think of these as web pages. You might not want to consider these as web pages. You might want to consider them as different states. So it might not make sense for someone to ever just randomly go onto another page ever, given the context of the situation. But in this case, the damping factor makes sense.
Particular set. This model lets us now take any network of web pages and calculate the relative importance of those pages. In the first few steps the random surfer takes, the numbers aren't particularly accurate. A lot is based on random chance.
Law of large numbers, so...
But with enough time, the random surfer will continue to explore more and more, and the numbers will eventually converge to a stable PageRank value for each page.
Good, yeah.
And those values can then be used to determine what order search results should appear in, with the more important pages appearing first. PageRank isn't the only way to calculate the importance of web pages, but it's a pretty effective way, and it ensures that, for the most part, when you search for something, the results you get are hopefully the results you actually want.
Yeah, so I think that was a nice overview of the PageRank algorithm. The problem is it didn't really talk about any of the math. I guess it talked about like the simulation behind it, but you can imagine, like, is it really ideal to continually run a simulation every time? Like every like couple months or seconds or whatever to figure out the new true probability PageRank. New web pages pop up all the time. It's not really feasible to just continually doing this random surfer method all the time. I'm actually going to show you a way you can actually get these probabilities using math like a math equation instead of just using this random simulation model. And the good part about it is if you do the random simulation model versus the actual just math equation, they should be the same. Like, so that's like a sanity check right there, which I think is really fucking cool. One thing you didn't get into was like this structure of having a bunch of nodes and lines. What are these called? So this whole structure is actually called a thing called a Markov chain. And Markov chains are essentially just states where each state has lines connecting to other states, and each line represents the probability from going from one state to another. That's all it is. So one thing I actually did, because I got real into Markov chains at one point, don't ask me why, and I tried to find a visualization model which I liked, which could like let me insert different CSV files and like actually just like import and actually test my own CS Markov chain models. And what I realized is I didn't find one. The only one I found let me do like one for like 5 nodes max. And if you're doing something to simulate like web pages, I'm sorry, 5 nodes max is not it cheap. So one thing I actually did, I actually made my own. You can click it. It's really cool. I think it's really cool. I'm really proud of this. Okay. Some people said this looks like complete and utter dog shit, which I don't agree with. It gets the job done. Anyway, what does this represent? So essentially, you can have these different states like A, B, C, D, E, whatever. And then this one here. So this one right here from A to B represents, if I start at A, my next state, there's a 100% chance I'm going to go to B next. And then this one's also 1, so there's a 100% chance I'm going to go to C, and then et cetera, et cetera. So that's the idea here. So down here, you can actually get, because of math stuff, you can actually figure out an equation to actually figure out the expected visit percents. See, I didn't have to run anything like at all. So I stop, I reset, I do one step, and then it just tells me the expected visit percents because you can just figure that out mathematically. You can also use math stuff to figure out the expected first arrival step. So basically means if I start at like A, for example, how many steps on average will it take me to get to B? And it tells you right here, which I think is really fucking cool. I even made it so you can change the initial probability. So I can change that up right here. We get like 50% chance I start at A and 50% chance I start at C. We do that and then you step. It changes things accordingly. Still always should be 100% chance end up at E because this just loops around. Yeah, you run a bunch of simulations this way. And because of this math idea that they figured out, this math equation, this PageRank algorithm they could do mathematically, able to just like figure out the ranking for each one very quickly. So you can just import a CSV file, which represents all your different pages. Then when you do that, get the expected visit percentage and then just rank it like that. If you think, hey, that might not be right, you can just then do a simulation and then run it and make sure they match over time. So I actually import like an example real quick. So right here, there's a Markov chain that represents the weather. So this represents when it's going to rain. This one represents when it's going to be sunny. If we just look at the percentages. So right here, we have sunny to sunny is 0.9 and sunny to rainy is 0.1. So basically it's saying that if it's already sunny, it's a 90% chance that the next day is also going to be sunny. Or it's going to be a 10% chance it's going to be raining the next day. Then this is saying if it's already raining, then tomorrow it's a 50% chance it's going to rain. And there's a 50% chance it's going to be sunny again. So just by looking at this, what do you think the hunch is that? Is it going to be likely sunny more of the time or raining more of the time? What's your hunch? Think about that. So my hunch originally is that it's going to be sunny all the time. And let's see if your hunch is correct. What's up? Oh, we see the expected. Yeah, it's supposed to be sunny 83% of the time and rainy 16% of the time. We got that perfectly. Okay, we just got the math and did it. And we're running the sim, and we can run the sim, actually see these values actually converge to the expected visit percent. So we just going to do that for 1,000 steps, and these should be around 83 and a third and 16 and 2/3. And look at that. They're really close. Then you can change the initial probabilities, and the expected visit percent will change accordingly. So that's why I think this stuff is really cool. I think the idea that you can just have a whole list of different probabilities and different end states and then figure out just from some math stuff, which we'll go into next about more of the specifics. I know I'm being very hand-wavy here, but I just want to express kind of how cool this is, in my opinion. We can then rank them by how likely it is you'll end up at a page. And we can get even more specific and say, given you start at these pages, or given the probabilities that you start at these pages, these are the new expected visit percent, which I think is really cool. And we get even more in depth and figure out the average time, the average amount of steps it takes to reach that site, which I think is also a really cool thing. You guys have more data, other examples, which I think I like to show. Of course, there's a classes cycle. So what do you think the expected visit percent is going to be if we just continually go in a loop over and over again? Think about that real quick. Okay, now we're actually going to see what it is. And yeah, it's it's just a fifth all around. Of course, it's a fifth all around. So that's the idea of that. One other one I want to talk about before we go into the specifics about how this amazing thing actually works. So with stocks, you think that stocks have different types of markets. You can have a bear market, a stagnation market, or a bull market, you know, so whether you want to sell, hold, or buy. And you have the probabilities of the chances like, hey, if we're in like a, you know, buy market, what are the chances that the next day is going to be a sell market? If you have those probabilities, you can figure out the different chances that any given day would be that. Of course, this isn't actually how the stock market works. I wish it was this easy, but it's a nice toy model. You even answer like very interesting questions that I think are very hard probability questions that I think would be really hard otherwise. Some of these, you just have so many probabilities going on and you have to figure out like which one goes to which. It can get very confusing very fast. But if you have this type of model, then it's very easy. Here's one I actually made because I actually did it in real life. You guys may not know this, but I think about a year or two ago, one of my first streams was that I kept streaming. I flipped a coin and I kept streaming till I got 10 heads in a row. So the question I wanted to ask was, what's the expected number of flips I would have to flip the coin before I got 10 heads in a row? And one way it's kind of hard to figure this out is like, okay, you got a head, but then, oh, you got 5 heads in a row and then a tail, which means you have to roll another 10 heads. It's kind of like gets a little recursive, but with Markov chains, you can just make this whole thing. You know, you have a head 3x, head 4x. And remember, whenever you get a tail, you just go back to the start and then you just have to go all the way to this end with 10 heads in a row. So yeah, with this easy Markov model, you just, you know, do the math stuff, you run it, and then it just immediately tells you the percentage of getting there. And it tells you the expected first arrival steps, which in my case was the expected number of times should take me to first get there, which is 2046. Which I think if you actually watch the stream, which is really hilarious, no, I actually get it at 2043, I think. So I think so. If that doesn't show you this math is really accurate and perfect, I don't know what will. By the way, if you haven't seen that video, check it out. Check out the video. I think it was a torturous stream, but I think it was a good video, so you should check it out. So I've been pretty hand wavy with it. I think I'm going to explain it even more. How does this even work? How do you turn this image into numbers? This video right here actually goes more in depth into it. So I feel like this video is more of an overview, but I feel like this video is going to go more into mathy stuff. Spoiler alert, it's a lot of matrices. So
imagine a population of users navigating across a connected network of web pages. At any point in time, every individual user has choice to randomly pick another link to visit. The question we're going to focus on today is how one might define a ranking of pages based on a model of the web network. The particular model we'll focus on in this video is called a Markov chain, and what we'll eventually build to is an understanding of a remarkably beautiful algorithm called PageRank, which formed the backbone of Google search. As we like to do on this channel, we'll approach PageRank from a discovery-oriented perspective, where we'll naturally interact with powerful mathematical ideas involving these Markov chain models. Let's get started.
cool logo. Reducible.
A Markov chain is defined by a few specific properties. In the context of a web network, individual web pages correspond to states of the Markov chain. And going from state to state involves a transition probability. In this particular network, any user can go from state 3 to state 1 with transition probability 0.5. If a user is at state 2, they have a 100% chance of transitioning to state 3. In the context of web networks, it's common for transition probabilities to be assumed based on the number of outgoing links. For example, if a web page has 3 outgoing links, we assume the user is equally likely to transition to each of the states with probability 1/3.
Oh, I see. Well, that's not always the case. It makes a lot of math easier, but essentially they're just saying that like for these cases, if you have 3 links to 3 websites, you just want to assume they're all equally likely, which is definitely not true. If you're on YouTube, you're more likely to go to Mr. Beast's channel than like my channel or something. So it's just, yeah. Also, it's not immediately obvious. Like usually you're going to have all the percentages add up to 1. All the outgoing links add up to 1.
It is possible to also alter these probabilities based on some prior knowledge or data. So if we change the distribution as follows, it would assume that users are much more likely to click on an outgoing link to web page 2.
Exactly, yeah.
Now the problem we care about today is ranking the importance of states in the Markov chain. A simplified real-world use case here is to imagine a user got 4 web pages from a search query. These web pages will often reference each other, so they form a Markov chain. How should we rank the web pages to show an end user?
Visit percent.
First,
How do you get visit percent?
how to define the importance of a state in a Markov chain.
Visit percent.
If we have a variety of users surfing web pages, what might be a good way to rank the relative importance of each web page? Well, one natural way to think about the importance of web pages is to imagine a single user continuously going from page to page according to the Markov chain model.
The random surfer.
At each point in time, the user is going to be at a particular state of the Markov chain, and we could maintain a counter for the number of times they visit a state. Over a long period of time, the states that end up being visited more often can naturally be thought of as having a higher rank. In fact, rather than counts, we can think of this long-term behavior as a distribution on the proportion of time a single user spends in each state. In this particular Markov chain, if we run this experiment for a long period of time, the distribution stabilizes.
Yep.
And this distribution is formally called a stationary distribution of a Markov chain.
Yep.
Here, the stationary distribution indicates that the most important state is state 2, where the interpretation of the probability is that a random user who surfs this network for a long period of time will spend about 26% of their time at state 2.
Only a little
What we're
bit
gonna
more
dive into
than
in this
1/5.
video is how exactly might we find a stationary distribution of a Markov chain? In what conditions do these stationary distributions even exist? How do we efficiently compute them?
So these are all valid questions, but one thing I want you guys to really think about too is how can we express a Markov chain as numbers? Basically, I already spelled it for you guys, but the way you do it is with a matrix. There's a whole field of mathematics called linear algebra, which is just all about matrix math. I'm not gonna lie to you guys. The moment I found out about like PageRank and just Markov chains and just applications of them, that's when I thought this was really cool. This is a really cool fucking class. For the final for my linear algebra class, what we actually had to do, we had a problem, and from the problem, we had to make a Markov chain and then figure out the stationary distribution by hand. My teacher was such a geeker. He was so great. And the problem was so funny. I think I audibly laughed when I was reading it during the final. It's like you and the boys are trying to get as drunk as possible. It's like you're at this bar, you only have a 20% chance to go to this bar. You have a 20% chance to go to this bar and 50% chance to go to the hospital. It's just so great. Yeah, and also just like really made me this whole new field of math, which I just didn't know about. Just I thought it was really fucking cool, and I hope you guys are enjoying it too.
To get into how we calculate stationary distributions, we have to first understand how we can model Markov chains mathematically.
Yes.
A user might start at some initial state, and at each step, according to the model, they randomly transition to one of the possible next locations. At every step in time, there's a probability of a user being in a particular state.
Correct.
A natural way to model the state distribution at a particular step n in a Markov chain is with a vector of probabilities, where the sum of the elements in the vector must equal 1. Usually Markov chains are initialized with the initial state distribution at step 0.
Yes.
It's pretty common for the initial distribution across states to be assumed as
There's a lot of lingo. Basically, all it's saying is that pi of 0 would just represent the probability of just starting at a specific state. That's what pi 0 is. And then pi 1 would be the probability of being at that state after one step. And then pi 2 would be the probability of being at each state after 2 steps. And then pi 3 would be the probability of being at each state after 3 steps, and et cetera, et cetera. That's what this, I know this looks like a lot, but that's the idea of what they're trying to convey.
Uniform, which intuitively just means we expect the user to start on any web page with equal probability.
Which is not true in practice. You know, again, we're trying to make this an easy example.
One of the key aspects of analyzing Markov chains is understanding how the distribution across states change at each step or point in time. This leads to a discussion on how we model transitions in a Markov chain. Let's isolate state 0 of this Markov chain and think about how the probability of landing on it after one step works out. In order to make this calculation, we need to know the probabilities of being in each of the 5 states of the Markov chain at the previous step in time.
Correct.
Once we have these probabilities, the probability at state 0 is essentially a weighted sum. We take the probabilities of each previous state, multiply them by the probability of transitioning to state 0 from that state, and sum over all the states. If you think about this calculation, it's essentially a dot product. We can extend this across all states of the Markov.
So essentially this saying, oh, we have this initial probability state, right? The first thing is saying, oh, it's equally likely we start at any one. So each one starts at 0.2, 0.2, 0.2, 0.2. So 20% chance we start here, 20% chance we start here, 20% we start here, etc., etc. Now we want to know what the probabilities are after one step. So let's just say, what's the probability of being here after one step? So to figure that out, we basically need to figure out every possible combination and add them and sum them all up. If you noticed this before, this is pretty much what you do for a bunch of probability stuff. You kind of add up all the different possibilities and then add up the probabilities to figure out the total probability. In order to figure out what the chances you're going to end up here after one step, you got to figure out, okay, well, what's the chances I'm going to go from 0 to 0? Like, okay, I can't go from 0 to 0. Okay, so that's 0. Okay, well, what's the chances I'm going to go from 3 to 0? Whatever that is, you have to multiply that by the chance that you are at 3. So you multiply the chance that you're already at 3 times the probability that you're going to go to 0 from 3. You do that all around. So you say, okay, so what's the probability I'm going to start at 4? And then what's the probability I'm going to go from 4 to 0? And then multiply those together. So that's essentially what they're doing. So these numbers right here represent the probability that you're going to be here on that step, on the previous step. And these represent the probability that if you are at this step, what's the probability you're going to go to 0? And that's the idea here. Then you add all those probabilities up, and then that's going to tell you what the probability is for the next step, that you're going to be there at the next step. And you basically just do that for every single possible state. So you can imagine this gets really crazy. If you have way more than 5 steps, it gets a lot of computational. But lucky for us, these are just additions and multiplications and doing dot products, which if you don't know, is one thing we can do with matrices very well, very efficiently. So it's really great. It works out that way. So you do this a lot for probabilities. You kind of add up, you figure out all the different possibilities and then multiply the chances that those probabilities would happen. And by summing them up, you get the total probability. So that's just very common in just anything with probability stuff. I'm trying to think of an example off the top of my head. That'd be a little bit easier to explain. Oh, I got one. It's like, what's the probability of rolling two numbers that sum up to 7? So from that, you're like, okay, well, what's the probability I roll 1 times the probability I roll 6? Plus, what's the probability I roll 2 times the probability I roll a 5? And you add them all up. You add those probabilities together. You get the total probability of rolling a 7. That's the idea. And that's just the same thing here.
Chain. If we take all the transition probabilities from state to state and fill them into a matrix where every row index corresponds to the previous state and the column index corresponds to the current state, this gives us a transition probability matrix. Now, what's really nice about Markov chains is we can find the probabilities of landing in each state at the next step fairly easily. It's just a matrix vector product of the probabilities at the previous state times the transition matrix. Now, the problem of finding the stationary distribution can be formalized. A stationary distribution is defined as follows. Given a distribution pi, we define it as a stationary distribution if after the next transition, the resulting distribution is also pi.
And this makes sense intuitively, right? Basically it's saying, hey, we're stationary if we did an extra step and we didn't change it all. We're at a natural ending point. That's what it's saying. And remember what our pi represented. Our pi represented what the different states were. It was basically saying, hey, if I have my state and do the next step, if I end up with the same step, then we're at a stationary step. So here we just have an equation to solve. We basically have x equals x times p. Then we got to solve for x. And then x and p are just a bunch of matrices. So let's look back at what we did. Our original solution to this was to just run a huge random surf simulation like a bajillion times. And then by the end of it, hopefully we ran it enough times that we ended up on a convergent state. That was our original solution. But now, with the way he explained it, we now figured out a way to actually analytically and consistently get the exact solution, not an approximate solution, the exact solution.
If this is the case, no matter how many transitions occur after this point, the distribution across
stationary
states will never change.
Yeah.
So another natural interpretation of the stationary distribution is that given a large enough number of users transitioning across states, once we reach a stationary distribution, the proportion of users that lie in each state will not change. Note that users will continue to transition to different states at each step.
The amount of people in each state
Overall
won't
distribution
change.
of users across states will remain constant.
Exactly.
Before we get into exactly how we might solve for the stationary distribution, it's important to address the question of whether a unique distribution even exists for a Markov chain. And another critical point to address in our model is if any initial distribution eventually converges to the stationary distribution.
That's a fair question too. Sometimes, math is really hard. Sometimes you get really hard equations. Is it always possible to find a unique stationary distribution? Can you make a Markov chain that's so crazy that there is no, it always is random each step. There is no convergent state. What do you guys think? Think about that in your brains and think about why you think that. Because here are the two intuitions I'm thinking about. You could say, of course, this seems like pretty easy. I don't see like what properties you would need in order to not get a unique stationary distribution. As long as you can just put into a matrix, would you see no reason not to? The other thought could be, well, there's so many different possible Markov chains that surely at least one of them can't converge. So there are two schools of thought.
On ranks of web pages if multiple stationary distributions existed, or a stationary distribution changes based on the initial distribution of users among web pages.
Oh, that's a good question too. Do you guys think the initial probabilities actually change whether or not there is a stationary distribution? So let's say I have I have one Markov chain, and I start at state 1, okay? And that has a stationary distribution. Let's say I have the same Markov chain, but now I start at state 2. Do you guys think that'll still have a same stationary distribution? Is that always possible? It's basically saying if I start at any state, does that always mean it's going to converge eventually? Or is where I start actually like a huge factor in whether or not this will converge or not? Think about that.
Let's start with the question of uniqueness. I challenge you to find an example of a Markov chain where multiple stationary distributions exist. This may seem like I'm throwing you off the deep end here, so I'll give you a hint. Think about a simple example with only 2 states.
Define a Markov chain with multiple stationary distributions. Yeah, they're both loops. They're both loops. So it could be 0 goes to 0 100% of the time, and 1 goes to 100% of the time. Because then they'd have multiple they have multiple stationary distributions, right? That's the idea I'm thinking about. Because if you start at 0, then you always end up at 0. But you start at 1, you'd always end up at 1.
Suppose we had a Markov chain with the following transition probabilities. For this type of Markov chain, what's the stationary distribution? Well, if you think about it, given any initial distribution, nothing's really going to change because every state transition points to itself. More formally, the transition matrix is simply the identity matrix. So any initial distribution by definition is a stationary distribution. So this is where the first important constraint regarding Markov chains comes into play. This particular Markov chain has the property where if a user starts in one state, they can't get to the other. Other state. These specific Markov chains are called reducible Markov chains. I know what you're thinking. And the answer is no, I did not make that name up. In fact, what we really want for stationary distribution analysis is irreducible Markov chains, which have the property that
has a chance. Wait, what's his channel name? Geeking.
To be reached from any other state. It turns out that for any irreducible Markov chain, a unique stationary distribution always exists. Now, the next question for irreducible Markov chains is...
All right, so that's my thing. So remember, we can get to every other page from any other page, then there's a unique distribution. If not, then it's not unique.
True that any...
Not necessarily unique.
Distribution eventually converges to the unique stationary distribution. Let's take a moment to discuss what we mean by convergence. In this particular Markov chain, suppose we start off with the uniform distribution across all states. If we run our Markov chain simulation, after about 20 steps, we end up converging to a distribution which, take my word for it, is indeed the stationary distribution. Now what's remarkable is that for this particular Markov chain, I can start off with any initial distribution, say for example, concentrating all the probability in state 0, and I still
You still end up the same place, yeah.
on the same stationary distribution.
True.
This time it takes about 25 steps, but nonetheless, it still converges.
Yeah.
In a general sense, what we mean by convergence is that any initial distribution, after a large number of steps, settles into the
Large doing a lot of heavy lifting.
distribution. My challenge to you now
A lot
is
of
to
heavy
see if
lifting.
you can come up with a Markov chain where an initial distribution does not actually end up converging to the stationary distribution. This is a pretty hard task, but again, think about a simple two-state example. Here's the simplest counterexample. Suppose I have a two-state
Yeah, this makes sense. It's not going to converge. You're just going to keep cycling back and forth.
irreducible Markov chain where each state has a 100% chance of transitioning
Well, it's irreducible.
to another state. What's the unique stationary distribution?
It's irreducible though, since you can go to whatever state, given starting state.
The best way to see the issue here with convergence is with two initial distributions. If we start with the uniform distribution across both states, all transitions will result in no changes, and this distribution is indeed the unique
Yeah, but if it's anything else, then it's just gonna keep swapping back and forth.
stationary distribution. But what if the starting distribution was 80%
Anything
at
else.
state 0 and 20% at
Anything
state 1?
else.
Now, if we apply transition,
It's just gonna
the
keep, yeah.
distribution across states never converges. It simply oscillates between the two extremes. This brings to light a second key property of Markov chains. These types of Markov chains are called
Periodic.
Markov chains. We won't go too in-depth into periodic Markov chains, but there are a couple of things to know.
So example, periodic Markov chain, which I had was of course if you guys remember the cycle I showed you guys, there should be no steady state with that.
When discussing these types of Markov chains, we're implicitly assuming that they're also irreducible.
Sure.
The intuition behind periodic Markov chains is that if you imagine a user moving from state to state, there exists some regular interval greater than 1 between visits to a node. For example, in the above Markov chain, the period is 2, since for any starting state, it's only possible for a user to get back to the state in regular intervals of 2 steps.
Sure.
When Markov chains have this periodic property, it means that there exists some initial distributions that will oscillate rather than converge.
Yeah.
If no such regular period of greater than 1 exists for each state, we can say the Markov chain is aperiodic.
Aperiodic. So we want
Markov chains
aperiodic,
that are
irreducible.
and aperiodic
Yeah.
have an incredibly cool and perhaps surprising property that no matter what the starting distribution is, as you continuously transition through the Markov chain,
You'll end up the same
the
place.
distribution will always converge.
That is really fucking cool.
In our web page example, what this means is no matter what the initial distribution of users is across,
No matter what weird website you start on, you're gonna end up at Reddit. No matter where you start at.
web pages, as long as the Markov
You're gonna end
chain
up at
representing
DGen.
the web graph is irreducible and aperiodic, the long-term distribution of the users will converge to the stationary distribution, which, remember, provides a good metric to rank the web pages. It doesn't matter if all the users started out on a specific web page or if they were distributed evenly across all web pages. After enough steps, it is mathematically guaranteed to converge to the unique stationary distribution. This theorem is often called the ergodic theorem for Markov
I didn't know
chains,
that.
and it forms the basis of many applications.
Ergodic? I've never heard of that. I didn't. Maybe I learned about that. I don't remember the word ergodic. Eroge?
This
Ergodic.
theorem, of course, requires a proof, but the details require a fairly strong background in probability theory, so for the interested viewers, I will provide a good link in the description to the
Woo!
Now, the next
I'll read that
natural
later.
question, of course, is how
Maybe.
do we actually calculate the stationary
Yes.
distribution?
How do we solve x equals x times
The
p?
first way is perhaps the most straightforward method. We start off with an initial random distribution, and at every step we
just
multiply
try.
the Markov transition probability.
We just
matrix
try
with
everything.
this distribution. After we get the new distribution, we simply check if the distance between the new vector distributions is less than some tolerance that we choose. When this difference is small enough, we claim that we have
We're
found
good.
the stationary distribution.
Again, this is also
In a
just
sense,
like
we
random
consider
surfer.
this as a brute force method
Yeah.
to find the stationary distribution of a Markov chain.
You just keep going until you find it,
The
which
second
isn't.
way to solve for a stationary distribution
Don't
is
like.
to utilize the definition directly.
System of
When we expand the
equations.
definition, it features a system of equations, and if we can solve it, we have a stationary distribution. But there's one problem. If you try solving the system of equations, you will find that it's actually unsolvable.
Yeah.
Two of these equations end up being redundant information, so you can't find a unique solution. The trick to
Remember, you
solving-
have 4 unknowns. You need 4 unique equations. Well, by unique, I mean useful equations, not redundant equations.
Solving the system of equations is to add in the implicit constraint that the sum of the individual probabilities
You said you'd have
must
1.
equal
Yeah.
By replacing one of the Markov chain transition equations with this.
Was that redundant? Pi 3 equals pi. Oh yeah, it is. It is redundant.
By replacing one of the Markov chain transition equations with this implicit constraint, we can solve for the stationary distribution directly through a linear system solver.
Easy. We're really good at solving systems of equations. We just use matrix. We just use our row operations to figure out reduce the matrix.
The final method is my personal favorite because it's quite a cool connection between Markov chains and some fundamental linear algebra. To understand it better, let's modify our state transition equation slightly. There's an implicit convention to define the Markov chain distribution as a row vector, since it makes the transition probability matrix nicely correspond to the edges of a Markov chain.
Sure.
But another way to represent the updates of the distribution is through a more standard matrix vector product, where we now represent our distributions as column
You can keep it like
vectors
that
and then
too,
multiply
sure.
the transpose of our matrix by the distribution to update it. By treating every column of our original matrix as a row and multiplying by a column vector, we get the same dot
Should have the same thing. Yeah.
Once we have this
It's two
representation,
identical,
if you
yeah.
think about these column vectors on a coordinate plane, we can observe how the updates change the vector over the iterations. And what we're looking for is a vector where applying the matrix P transpose results in the exact same vector. Assuming that this vector always exists for this matrix, what does this imply about this special vector? What property of P transpose does it correspond to? A core concept in linear algebra involves
I remember this part.
eigenvalues and eigenvectors.
Oh,
An eigenvector V of a matrix A has the property.
I remember
that if you
eigenvalues.
take the matrix
I vaguely remember eigenvalues and eigenvectors. I remember having to find them. This is actually new stuff right here. I don't remember all of this.
vector product A times V, it scales the eigenvector V by a corresponding eigenvalue lambda.
Yes.
If you think about stationary distributions from this perspective, we're actually looking for a very specific eigenvector, the one that corresponds exactly to the eigenvalue 1. A remarkable fact.
Yes. We are trying to find the V. We are trying to find vector V when lambda is 1. Because that would make it the same, right? That would make it the same type of equation. Because then this would just be V, and then this would be A. Yes, that's correct. Yeah. So we are just trying to find whatever the vector is when the lambda value is 1. That's correct.
Fact is that for irreducible Markov chains, the state transition matrix P transposed always has an eigenvalue of 1 with a unique eigenvector. So a third method.
So eigenvalues, okay, I'm trying to remember. Please correct me if I'm wrong in the comments. I'm pretty sure you can use eigenvalues and eigenvectors in order to remake the original equation. If I remember it correctly, you can make the original equation the sum of the eigenvalues times the eigenvectors. If I remember correctly, I believe if you have a specific type of matrix, then you can reduce that matrix into just a dot product, a product of just scalars, a product of just eigenvalues and eigenvectors, if I remember it correctly. Yeah, I'm pretty sure that's it. Which I think it is a really cool property, that if for some types of matrices you can actually just reduce it down to just a bunch of a multiplication sum product. Yeah, it all goes back to dot products, which is just about them adding multiplications.
Eigenvector corresponding to eigenvalue 1 in the transpose of the state transition matrix. Once you have found this eigenvector, the stationary distribution is just a scaled down version of it that sums to 1.
Wait, what do you mean scale down version of it? Oh, with all of them added up to 1. Yeah. That's extra
This
constraint.
Markov chains in linear algebra really blew me away, and I wish it's one that...
Because I didn't know this either. Huh. Yeah, because I'm pretty sure the one I learned, the way to solve these by hand, I did the system of equation, but the idea that it's actually just eigenvalue 1. And it makes sense. Yeah, wow. The more you know. I think it's really cool.
that was mentioned more often in a standard linear algebra class.
I don't think I heard a lot of that in class.
Natural applications of the concept of eigenvalue.
Because you do a lot of eigenvalue, eigenvector stuff in linear algebra. Yeah, because I'm trying to remember if this is how they taught me how to solve these problems. I don't think it is. Wow, yeah, it's really crazy. Wow, no, I'm really starting to think. Yeah, wait, I think this is really cool too. Because if you spend like half the class learning about eigenvalues and eigenvectors, but then you're like, okay, well, now we're gonna do this different way to solve these Markov chains. But then instead you could just said, oh no, just do what you've been doing before with solving the eigenvalues and eigenvectors, but just solve it for eigenvalue 1.
Throughout engineering, you'll often see that long-term behavior of systems is intimately tied to eigenvalues and eigenvectors. Markov chains just happen to be one good example of that. So, to take stock of where we are, we have a stationary distribution, which is a good measure of the importance of every web page in a Markov chain.
Yes.
We now have 3 separate ways to calculate the stationary distribution. So here's an interesting question for you. Imagine we tried to find the stationary distribution of a massive web network of hundreds of millions of web pages. Which of these 3 methods do you think will perform best in practice?
The worst will be brute force. I'm trying to think. I think we're really good at doing systems equations, but I also think we're also really good at doing eigenvalues and eigenvectors. I think for mine, to spoiler alert for how I coded mine up, I think the way I coded it up, I solve the system first, and then I try eigenvalues, and then I try brute force, and then none of those work, I just state nothing. I think that's how I set mine up. But maybe eigenvalues is the way to go. Actually, now that I think about it, I don't even know if my code does eigenvalues or system of equations. I don't really know what they're doing on the back end now that I think about it. I just say solve this equation. They could be doing system of equations or eigenvalues in the background. I don't even know. I'm going to guess systems of equations. I know brute force is last.
Let's say we tried solving a system of equations on this massive...
That's eigenvalues.
The big problem here is in practice, solving a large system of equations can be quite expensive.
Yeah, but that's not how you solve it.
Linear systems tends to be a cubic time operation, which can be pretty slow when dealing with the massive scale of web networks. The eigenvalue method also has a similar problem in the sense that, in general, getting a decomposition of eigenvalues with eigenvectors takes cubic time. So perhaps shockingly, practical experiments on web networks...
I was wrong. No.
Method of calculating the stationary
no.
often led to the best performance.
Oh my god.
It turns out that a lot of web networks have...
Well, if that doesn't prove I don't remember this video. I'm really shocked about that. Is really just testing it just really just the best way to go? I guess that makes sense. Does that make sense? Why didn't I say brute force? I said brute force because brute force just doesn't give the exact solution. It gives an approximate solution. But then again, for this, do we really care about the exact solution for these? I guess not. We really only care about the approximate solution. It's not like it's like, what? There's actually supposed to be 25.2% chance you visit this site, but you said 24.9, you know? Is anyone really going to care if the ordering is like pretty much the same? I guess not. I guess it doesn't really matter because we're just talking about the ordering. It's not like we need exact solutions here. It's not like it's a rocket scientist where like it's like, hey, we really need exact numbers at like a certain precision level. Approximation is like good enough, I guess. I guess that's how all of our tech really is going. It goes back to AI. We don't get exact solutions. We just get good enough. I guess that is how journey of math, isn't it? We just take the good enough solution, yeah. Now that I think about it, I guess I do just use the exact solutions for mine because for mine, I want specific exact solutions. Because if you do this in practice, right, you don't really care about the exact solutions per se. You care more about the ranking. But I think for my site that I made, I actually care more about the exact solutions from the ranking. So I guess that makes sense. More you know.
Relatively fast convergence times. Most web search use cases converged within 50 iterations.
That's not a lot.
Now again, this depends a lot on the thresholds of how much tolerance you have for error.
That's true.
The answer that you get in 50 iterations is not the true stationary distribution, so we are cheating a bit, but it goes to show the trade-offs that engineers were willing to make for something that is good enough.
Yeah, but we don't. Yeah, the
Sometimes-
idea is that we don't need the exact solution. But if we only care about the ranking, then yeah, brute force makes sense. But we want exact solutions, and because brute force will never give you the exact solution. It'll only give you an approximate solution based off your tolerance level. But we don't care about that, then yeah, brute force. That makes sense.
Force approximation beats out clever algorithmic transformations.
I fell
This
for
is
it.
just an excellent example of an engineering mindset. In some cases, a good enough solution is a better choice than the perfect solution.
Yeah.
The PageRank algorithm that built the first version of Google is fundamentally based on the principles of calculating stationary distributions of Markov chains. But there are a few important complexities that the creators needed to address. After all, web pages can do whatever they want, and
Again, if it's not obvious enough, the PageRank algorithm is definitely like more evolved. Google has so many other statistics and things they also incorporate into their PageRank algorithm now. But yeah, I'm pretty sure the original PageRank algorithm in theory is like an exact solution, not an approximation.
one type of Markov chain that gives stationary distribution calculations a problem is web pages that have no outgoing links. As a result, all transitions to the state would never exit the state.
Yeah, and it would eventually go to 100. Yeah.
The ranking of the pages properly, since eventually all users traversing this network will just be absorbed into state 3.
Yeah. That is the natural end state. Yeah.
Another issue occurs on the following type of graph. It's entirely reasonable to have 2 or more web pages linked to each other in such a way where once a user enters, they get stuck in a never-ending cycle. Once again, if we try to
How my class learned how to deal with these types of things, instead of treating like state 1, state 0, state 2, and state 3 as 4 different states, you actually treat this whole system as 2 different states. Because the idea here is once you get to 1, you're going to be in this loop forever. You're going to be in loop hell. Then once you're in this loop, you're going to be, actually no, you're not in loop hell there. Up here, you're in loop hell. You're never going to get out. You're never going to get out of here. So what I learned in school is that instead of treating this as like 2 different states, you actually treat this whole like 1, 0 as just one state. You just treat this whole thing as just one individual state, and then these 2 as individual states. The idea is like, oh, we're stuck in this one state. That's how I learned about dealing with it in my undergrad, but maybe there are other ways to deal with it.
do some sort of stationary distribution calculation on this network, it's impossible to rank the states since all users eventually just end up cycling between states 0 and 1. The big problem here is that a lot of our tools for calculating the stationary distribution and subsequent ranking rely on the underlying assumption that we are working with irreducible and aperiodic Markov chains.
That's true.
The question now is, how should we handle Markov chains that don't fit this property? The idea is remarkably simple, and it's a classic example of transforming a hard problem into one that we know how to solve. Let's think about this from the perspective of someone who surfs the web. Suppose a user ends up continuously transitioning to various web pages and then suddenly they hit a web page without any outgoing links.
Hey guys, can't
What might they do? Well, it's reasonable to think that they'll probably just find another web page.
They'll randomly go to
from the
another
network. In more technical terms, they'll randomly select a new state from the Markov chain. And the way we can embed that idea in the Markov chain is really elegant. Going back to our earlier simpler example, the core solution is, at every step, with some probability alpha divided by the number of states, we'll end up
just have a
transitioning
damping
to
factor.
any random
Yeah.
state in the network.
Just have a damping factor.
You can think of this as a way to simulate the notion that a user might just get bored and go off and open a completely random page and then
Which makes
start
sense for
searching again.
PageRank, yeah.
Now, it's not enough to just add these random transition probabilities because you'll notice that it breaks the assumption of a probability distribution across transitions. Notice these distributions no longer sum to 1.
Yeah.
So what we do to solve that problem is we add a damping factor of 1 minus alpha to all the existing transitions. In a sense, with probability of 1 minus alpha, we'll follow the original Markov chain transitions, but otherwise, we'll randomly teleport to a new state. This basically prevents any state from permanently becoming an absorbing state, and it also prevents users from being stuck in a cycle as well. Mathematically, what's going on here is we take our original transition probability matrix, multiply by the damping factor, and then add alpha over n times a matrix of all ones. Adding the weighted matrix of all ones simulates the idea of any random state being picked as the next transition. All PageRank involves is calculating the stationary distribution of this modified Markov chain. Throughout this video, we've discussed Markov.
Yeah, it's really smart, you know, especially for websites. So it's definitely more likely, like how real life is. You're just randomly going to go to another site. Sometimes, like if you have an absorbing state, you know, that's just how the natural state is. You're not just randomly going to go to another one. Sometimes in real life, there is an absorbing state where you're just going to end up most of the time.
Which implicitly requires some background in probability. One of the best ways to learn probability and solidify
we got the W add
concepts is by interacting with them directly and solving hands-on problems. PageRank then tries to find the stationary distribution of a which can be interpreted as a Markov chain.
And we turn it into a
Find the stationary distribution of a slightly modified Markov chain where the transition probability matrix is updated by a damping factor and also accounts for random state transitions.
Yep.
This final matrix is what PageRank then uses to calculate the stationary distribution by
using
performing
brute
iterations
force.
until the distribution converges up to a tolerance. This final distribution then provides the information
we have the
needed
ranking.
to make a ranking for web pages. It's not an exaggeration to say that PageRank may be not only one of the most
it probably is. It probably is. Yeah.
also one of the most important in terms of defining the
I know there's a lot of information. If you understand the basics of how we got here, it's only 4 steps. Like there are a lot of concepts to understand. Like you need to understand what a Markov chain is. You need to understand what the damping factor is. You need to understand like what a steady state is. But if you understand all these concepts, this is actually pretty easy to understand. I shouldn't say that. I shouldn't say pretty easy. I say easier than you may think. I know when I heard about this, I feel like I had this moment where I'm like, this is the algorithm. This is the algorithm that runs pretty much like runs most of the internet. I think I'm going to show the code actually.
needed to make a ranking for web pages. It's not an exaggeration to say that PageRank may be not only one of the most lucrative algorithms ever created,
For
but
sure.
also one of the most important in terms of defining the domain of search. Most of you now know the remaining parts of the story.
Larry Page.
Sergey Brin went on to found Google.
Larry Page, that's right. PageRank. It's a double entendre. You got it? I'm not making that up either. It is. That's what it is.
And the rest is history. Thanks for watching, and I'll see you all in the next one.
Good video. Good video. The most important algorithm ever. So one thing I want to pull up is actually rank wiki. This is it. This is the code. This is Google. This is Google. This. What's that? 1, 2, 3, 4, 5, 6, 7, 8. 8 lines of code and then testing. 8 lines of code runs 90% of the internet. Obviously not, but you know, hopefully that makes the point. This is like deceptively simple. I think it's really cool. And yeah, mine doesn't really have the damping factor because I wanted to do like any Markov chain, not just like specific pages. You know, if you want to do damping factor, you gotta do that on your own. But you know, maybe I should add that. Those are Markov chains. $1 trillion algorithm. I don't think that's an exaggeration. It probably is one of the most important algorithms. Definitely up there. Definitely top 5. So I think it's really fucking cool. I hope you guys learned something. That is STEM Tuesday, where we hopefully you learned something. I learned something, and yeah, we're gonna learn more stuff. The first of many. So hope you guys like the stream, and I think probably call it a day. Have a good one.